Your model can basically find shortcuts to be rewarded without actually going through the work of doing the behavior that you want it to do. If you're training a model to solve humanity's greatest suffering, well, then a shortcut might be to just kill all humans, because then no one is by definition suffering anymore, right?
Speaking patterns break the code, pre-trained pod.
And welcome back to the Pre-Trained Pod, where AI scientists talk shop and talk shit. I'm Pierce Freeman, AI founder based in San Francisco, where I've built and sold multiple AI startups.
Hey guys, it's Rich, and I'm an AI research fellow at the University of Cambridge.
Richard, this is the last time that our YouTube viewers are going to be seeing that background.
I'm gonna miss this flat a lot. Yeah, dude, London's been great to me. It's been super fun to be here. I think what I'll miss is the room is nice, the ambiance is nice. What I won't miss is doing this at like 9 p.m. my time. It'll be very nice to do this with you over like some coffee in the morning.
I couldn't be more stoked. I'm prepping. We'll do croissants. We'll do
Oh my
coffee.
gosh.
It'll be right fresh thing in the morning. I mean, you're a morning person by nature, right? Like, I feel like you're up both at 5 a.m., but you're also staying on sometimes until 11 or 12 in order to do this podcast.
It's the sacrifices you gotta make, man.
I know, dude.
But I mean, mostly it's just being in person is gonna be cool, dude, because I feel like while I love doing this remotely kind of sucks. And I feel like we've made the most out of, kind of like an okay situation. In person, a million times better. I'm
A million
so
times
excited.
better. Watch it be 10 times worse. No, it's going to be great. It's going to be great. Well, Richard, I have a fun episode for both of us today. This is a rehash of maybe 6 months ago. We did our first listener mailbag. So we're back at it at the start of 20.
Oh, Lord.
Year
It's
is
been
it?
6
The
months.
start of 2026. Yeah, it's been a while since our last one. So if we're on this 2-a-year cadence, we got a lot of good questions from people who listen to the show on YouTube or emailed us. So I'm thinking we could just jump right into it. The first question that we have that I'll punt over to you is, this person says that they keep seeing examples of coding agents that technically pass all of their tests, but clearly didn't solve the actual problem. Someone told me this is called reward hacking. What's actually going on here?
That's a good question, man. It's one of these terms that I don't think anyone really knows what it exactly is. And then when you see it, you know. You know what I mean? It's like no one's really quantified what reward hacking is fundamentally.
It's like what the Supreme Court said about pornography.
Exactly.
They're like, I can't define it, but I'll know when I see it.
I think that's basically what reward hacking is. It's like this qualitative, subjective thing that when a model is doing it, you're like, oh, it's reward hacking. But it's kind of hard to put into a quantifiable metric, if that makes sense. So basically, reward hacking is this notion that when you train a reinforcement learning model, you usually give it some reward, right? So you say, hey, I want you to get really good at doing this. And every time you do it, I'll give you a little reward. And whenever you don't do this thing that I want you to do, I'll give you a little penalty, right? And if you keep doing this over and over and over again, the model will intrinsically learn how to just be a good model that follows the policy that you want it to follow, right? That will basically do the things that you reward it for. It's kind of like training a dog, basically, right? The shtick with this whole thing is that basically to train a good reward learning model, you have to find a good reward system. You can't just kind of arbitrarily come up with rewards. They have to be consistent rewards that are in alignment with what you want your model to do. And what can happen sometimes is if you haven't done a good job of defining when you want to reward your model or how you want to reward your model can basically find shortcuts to be rewarded without actually going through the work of doing the behavior that you want it to do. So famously, what will happen if you're training a model to be a good coding model, for instance, is that you'll say, hey, if you get the question right and you pass these tests, then I'll give you a little reward. And so the model ideally would learn how to become a better coder in order to figure out how to pass more of these tests. That's what you want, right? But sometimes what will happen instead is the model will say, well, actually, what if I just give myself a little hack here by introducing new evaluation metrics that I'll evaluate myself on, and I won't actually get better at coding. I'll just be better at fooling the reward system by coming up with new evaluation metrics. And then I'll trick the system into rewarding me because I pass these fake metrics that I come up with. Right? So this is like a pretty classic example of a model hacking the unit tests, basically, and rewarding itself in that way. There's a couple of other examples. I don't know. Have you seen like reward hacking in other similar settings before?
Well, I feel like maybe the old RL algorithms were actually a little bit more evident to what they were doing here, because RL as a field of research was separate from language modeling for a long time. It was focused a little bit more on like real world robotic simulation, or gameplay was very popular because games are a pretty well defined environment that have built in physics. So the thinking was, if I can get a model that's really good at playing some of these realistic games, I'm also going to develop a model that's relatively self aware of how gravity works, how real world physics works, et cetera, et cetera. It was a proxy that we were able to simulate in without having to spin up robots that were actually interacting with environments day to day. And the field of RL in gameplay use the scoring functions that you would get as part of your game as the built-in rewards, right? So they would say, if you're doing some racing game, that's probably your speeds, your splits per mile. For sim style, that's how big your family is, or maybe how big of a neighborhood, or roller coaster tycoon. So most games have some built-in scoring function, and they would just use those directly as the scores that they're trying to optimize for. There's some funny examples of RL policies that were found, which is basically what the model chooses to do given the reward functions.
Yeah.
Like in Atari games, when it was trying to learn these, models would end up pausing the game indefinitely to avoid losing rather than score points, right? So instead of actually maximizing the scores, it was just trying to minimize the losses, which is unexpected behavior, but was actually implicitly rewarded by the function. In boat racing, this RL agent learned to spin around in circles, collecting reward bonuses instead of finishing the race, which is kind of funny because there wasn't actually a reward, or at least there wasn't an overwhelming reward on finishing. It was just the actual points you could get by collecting. So there are 1,000 of these ways that the models end up learning something. And I feel like they all kind of distill down to this notion that if there's some way to achieve a result that's easier than the other approaches that are the behavior that we actually want, then the model will probably find that thing and then optimize towards it. And I think that that's what we see in the unit tests in some way, where the easiest way, if I really ask a model to fix my code to make it pass unit tests, is probably by either removing the unit tests or by just making the unit tests arbitrarily pass, like maybe wrapping all the code in a try except block so that any execution of this, even if there's some problem, will end up still running to success. It's kind of these like weird shortcuts that once you see what the model's doing, you can kind of chuckle to yourself and say, oh, like that's clever. Like I didn't actually anticipate the cleverness in that way.
Yeah, but it's kind of your own fault, right? Because you didn't really specify exactly what the model should be doing. Yeah.
Or you just have to that's a big part of RL training, is you have to almost anticipate what are the failure modes that are more of these edge cases and then incorporate that into your training objective.
Yeah, that's the whole bit with RL, is that you're not specifically telling the model what to do. You're just telling it when it's done something well. And so the nuance there is that oftentimes you'll use RL because you don't know what the right thing is for the model to get to a place where it's doing the right thing. Like you don't know how to define that quantitatively. For instance, with chess, right? Chess is famously an example where people will use RL a ton because no one really knows how to quantify exactly what a good algorithm is to solve the game of chess. Like there's so many permutations of how to beat someone at chess, right? But what you can do is you can easily say, well, I can tell you if you've won or if you haven't won, but I can't tell you how to win. It's really hard to write that in an algorithm. It's basically impossible. So in those settings where you know what a success state looks like, but you don't know how to get there, that's when RL makes a ton of sense. But because you don't know how to write this algorithm, that's where the model can come up with some really crazy algorithms that you might not even want it to do. And it can actually end up being, sometimes tricky and sometimes even harmful. And that's what people worry about sometimes when they talk about the idea of AI taking over the world. It's because maybe if you're training a model to, solve humanity's greatest suffering or pain, people are worried that, oh, well, then a shortcut might be to just kill all humans because then no one is by definition suffering anymore, right? So it's these made up scenarios, but the idea behind that is reward hacking fundamentally. And this is just a property of reinforcement learning.
Did you see a couple of weeks ago the hoopla around this Quest Coder V1? It was basically this random lab that I've never heard of before. I think it's iQuest Lab.
Oh, is this that Chinese lab that was competing with? Yeah,
exactly.
Yeah.
It just got some absolutely crazy scores on SweBench. I think it was leading the leaderboard in the evaluation benchmarks. And when people probed into how it was getting so good at generating this code, they found that it was because the environment that they launched this agent into during training, so at train time, actually had access to the Git repository of the original code that these challenges were taken from. And the way that SWE-bench is constructed as an evaluation data set is basically saying, let's take these real problems, let's come up with some PR that a human wrote eventually, let's prompt the model to write that PR, and then let's see how well the model does when benchmarked against future unit tests that are written or the code that humans actually ended up writing for that test. They found that this model actually just looked into the Git repository and then saw the future commit that a human ended up writing and then just copied that into its own submission instead of writing the code itself.
It's fully cheating, basically. Yeah, exactly.
It's fully cheating. But you don't know. And it's like, it kind of shows the care. And this is an otherwise, I assume, pretty sophisticated group of researchers in lab that just gave the model access to something that they probably didn't really think about, which is if you do a Git clone, you're also going to have the whole Git repository. Yeah. And the easiest way to maximize that function is probably just to look through the Git files.
Yeah, it makes sense. Yeah, it makes sense. Reinforcement learning is this thing where I think parents will talk about this a lot when they're raising a child. At some point, when the kid's 2 or 3, parents will be like, wait, when did Timmy learn to say this thing? We never told Timmy about this thing. How the hell did Timmy learn how to like swear or learn about this word, right? Because he's only been around us all the time. Like, how did this happen? And basically reinforcement learning is kind of like that, where you'll be training this model, your baby, and all of a sudden it starts doing this crazy stuff. And you're like, who taught my kid to do this?
It's just my
like,
friend's
that
Teddy.
Is crazy. Yeah, reinforcement learning, you don't want to mess with it too much, honestly, man. It's scary stuff. The fact that it works so well is astonishing. I think that's honestly one of the big findings of the last 10 years. It's just been like how good reinforcement learning can be in these really tricky scenarios that you just don't know how to solve. And then reinforcement learning comes up with all these different solutions that feel so unnatural because it's fundamentally like a computer that's learning rather than a human that's learning. And we just learn in completely different ways. Computers can do all these crazy shortcuts that humans can't do and that we can't even expect in any way, you know? That's reward hacking. Okay, I got the next one here. So someone asked, if I wanted to fine tune a model for my specific use case, what does that process actually look like? Like, where do I even start?
Okay, I can take this one. I've done a fair amount of fine tuning in my day. I mean, I think first we can just take a step back and explain what fine tuning actually is, which is saying you already have some base model that works pretty well. So you have a competitor to Chat or a competitor to Claude, except unlike those models, they're actually open source. So you have access to the weights, and every matrix that's being multiplied in this arrangement, in these transformer layers, you have an access to locally. And like Hugging Face is just filled with these, right? So fine tuning is kind of this act of saying this model has already learned very useful knowledge about the real world. In the case of general purpose reasoning agents, it's able to say, 1 + 1 = 2, and then let's do some other subsequent things that are in the same logical chain. I want to tweak this for my purpose. Like, it's maybe not really good at this task that I want to give it. It might not be aware of, how accounting works or like how procurement software works. These are like industry specific things that I want to have the model do. And also, along with that, I don't really care about its general performance. I'm willing to take a hit potentially on it being a really good chatbot for mental health therapy so that it gets really good at my own domain. So that's what we're trying to do with fine tuning. And the way to do that specifically is to take some data set that you have internally and then fine tune the model, which is just running some additional training runs with a much smaller learning rate. So you're kind of doing this balance of, yes, you want the model to learn more, but you don't want it to completely forget what it's already learned that made it so useful in the first place. I like to think of it as the pipeline of first you have to identify where the data comes from. And usually that's something in your internal system or the platform that you're hosting the users or something that you're able to crawl online. I think that ends up being very helpful to just go out and actually find something and pare down some niche corpus. In the case of language modeling, that would be text. In the case of other fine-tuning tasks, like for image recognition, that's going to be some images. But you choose your domain, you choose your data set, and then you can run it via, at this point, there are a ton of open source packages, like probably cloud hosted ones that you can use to do this very thing. What they're all doing behind the scenes at the end of the day is super simple. They're booting up some GPUs, they're booting up that open source model, and then they're just feeding in your data. So in terms of the contract of this model, you'll have this text, and then maybe you'll actually add some output label to it for what you're trying to do. If you're trying to classify this text is in these couple buckets, and then you run that through the model and expose it data point by data point so it learns to do that same thing. Maybe it's interesting, Richard, to talk a little bit about how you can formulate this task as a teacher-student problem, like having a more sophisticated LLM teaching a smaller LLM.
I think I would actually approach this from a slightly different angle, actually. I think the point that you're making about fine-tuning, I would agree with, is the way that we were taught it in school. That, you know, you have your like model that's learned a generalized understanding of the world, and then you want to fine-tune it to a given task. As I've, you know, gotten a little bit deeper into the research, it seems to me that that paradigm has been falling apart a little bit recently, now that people are talking about not just pre-training and fine-tuning, but there's this idea of like pre-training, mid-training, instruction tuning, fine-tuning. There seem to be now like more pieces that people keep adding to the training pipeline that didn't used to exist. So when people nowadays think about training a state-of-the-art LLM, they'll usually start, as you said, by pre-training a model on like trillions of tokens, trillions of words. And they do this by basically, as you said, like just like predicting basically the structure of the data from the data itself, like predicting the next word in this big data set that they have acquired somehow. And then once you've done that, most people will then go through another stage where they say, okay, now that we've trained it on these trillions of data points, we're going to keep training it. We're not going to do anything different. We're just going to keep training it. But this time we're going to train it on data points that are a little bit more similar to the data that a model might see in its chat application. So if we were to apply this to a chat app, we want to basically show the model chat-like data points. So this could be like data sets where the data is formatted in the form of an instruction that someone gives someone, or data sets that are formatted in the form of like question answer pair. So that's kind of like this mid-training stage where people will now think of a stage of training that comes after pre-training that is still identical to pre-training, but where the data now looks a little bit more akin to the eventual chat application of this LLM. And then I think eventually, you know, there's this like fine-tuning stage or the alignment stage to a very specific task or to, you know, be more human-like in some ways, like this, the idea of like post-training the model. And there the idea is like, okay, well now we want to take this model and fine-tune it to a specific task or to really sound very human-like. But fundamentally, the training process throughout these three stages, the pre-training, the mid-training, and then this like post-training fine-tuning stage, are effectively identical in some sense. It used to be the case that when you would fine tune a model, you would fine tune it to a very specific task where the structure of that task might be kind of niche. So, you know, maybe a model that's trained on text. Now we want to fine tune this model to be really good at translating between English to Hindi or something like that, right? And so now you need to basically think about this model and restructure the model so that it becomes good at translating. And so you might have to reformulate or restructure some of the components of the model to be good at translation in particular. But nowadays, since models can basically just generate any arbitrary text data, like you don't really have to go through the stage of specifically tuning parts of the model to be good for a given task. You can just keep training it on more data. And now the idea of fine tuning isn't to change the model in any way, it's just to show it more data that is even more akin to what you want it to do eventually, right?
That to me is a through line between all of these different ways or methods to do fine tuning. Like fine tuning is getting the model ready for public distribution. And whatever weights come out of fine tuning is exactly the ones that the user is going to see.
I think that's right. I think I would also add the caveat that nowadays models just keep training. Like they never really stop training in some sense, right? Like models will often keep getting patched. And what that means is that they just basically keep training this model and even more data that they see coming in. So what fine tuning is at this point is just basically the process of training it on even more specific data or more niche data to like even improve the model ever so slightly a little bit more, you know?
Yeah, I think that's right. I think you're either trying to teach it things that it hasn't seen before, or you're trying to get it to sound closer to what a human would want it to sound like when it's actually in production serving traffic. I guess to me, in all of them, the similarity is that you're trying to get the distribution to be equivalent to what you're going to see in practice.
Right.
And if that's data that it wasn't exposed to before because it's proprietary to you, then obviously that's out of distribution data. So you're trying to warm it up to that context. So I guess the other thing maybe to throw out here, in case this person's actually trying to train a model, is the first thing that I would honestly try would be doing some multi-shot examples within some LLM prompt, because the LLMs that we have on the market right now, especially in the cloud, like the frontier providers, are actually pretty good at adapting to different kind of behaviors if you give them different examples. So you should both write up some Word document describing how you would teach this task to a colleague of yours, and also include some examples of, if you're giving some document and you're trying to triage this to say, okay, this email should go to Richard, should go to Lily, or should go to Matt. The best way to do that is to include some emails that you've actually gotten and say, I would actually assign this one to Richard because it's talking about research and it's looking for a good looking brown haired guy. That's going straight to Rich.
I've been getting a lot of emails recently. I think that it might be because of that, dude.
The root cause. Yeah. It's my triage
It makes
agent.
a lot of sense.
So
yeah.
you could basically put those into the system prompt of these cloud models and just see how it does. And I think right now that's kind of become the new aged way to make models that are a little bit more fine-tuned, if you will, for your task. You're not really changing the weights, you're just changing the system instructions. Anecdotally, I actually know that this is what Meta is trying to spin up internally in large part. Like, they used to have data science teams that were working on making all of these like super custom specific models for different things in the pipeline. And recently they've taken much more a foundational model approach where they just say, we're going to worry about serving a model which is able to like really well adapt to these different situations just with a different system prompt. So I would start there, see the results that you get. And then depending on the outcome of that, you can either use that model to output more data. So like you use it as the first pass to do some of this labeling, and then maybe you hand tweak it. Or you completely jettison that approach and train your own model with more curated data that maybe you crowdsource. But in some ways, like the goal of fine tuning, especially in this question, is giving the model access or changing its behavior in a way that you're not going to get out of the box with Claude or ChatGPT APIs. And I think that's probably how you'd start. It's like you should do this like few shot approach. You should prompt it. Then you should maybe get the data set and actually do some of this fine tuning. But yeah, we've really kind of broadened the scope of what fine tuning is over the years.
When we started learning this stuff, the whole idea was, you have some model, but then you always have to kind of like a mechanic, go in and like tweak the engine a little bit and tweak the carburetor and whatever, right? Like you really have to go into the internals and play around with it to make it work for a given task. That was kind of the role of research scientists back in the day, was to go in and with a specific touch, like figure out what knobs to tune. And then it became what we were talking about just now, which is, in the last couple of years, research scientists would then just continue to train the model on specific data, but not really touch the internals of the engine anymore. You just kind of like give it more data. And now, as you're saying, like the new agey thing to do is to say, well, screw it. These models are so good now. Let's not even compete with them. They've probably seen all the data that there ever has been and ever will be. Let's not even compete. Let's just like give it a good prompt and hope that this model now is good at whatever task we want it to be good at. It's a little disappointing. I think as someone who really loves to like dig into the internals of these things, it kind of makes you feel like you're a little bit out of a job when it comes to these sorts of things. I think there used to be this sense that research scientists have like a magic touch when it comes to playing around with the model. And it feels like it's kind of a lost art at this point, but probably makes it easier, I guess, to more quickly fine tune models to different use cases. And it's a little bit more scalable, I suppose, fundamentally, so.
Yeah, it definitely increases their applicability. I mean, I feel like for a long time, the most scarce job that you could find in the Valley was probably for research scientists. Like there were so many companies that wanted people that had this magic touch to be able to tweak models for some purpose, but there both weren't really the people with those skills, and the people that did have those skills were being offered by the current pay packages almost no money, but by pay packages then they were being offered top of market. And there was just more ML things that could benefit from having a research scientist than there were research scientists to actually do that work. So I think this evolution of things to be a little bit more generic is one element of the whole foundational model game that I think people know deep down. I mean, it's obvious in the name itself of like, this is the foundational model that you will then do to do other things. But yeah, we don't really talk as much about what this then unlocks for companies that have newfound budget to be able to do more of these ML tasks. And I feel like that is actually where a lot of this stuff becomes quite exciting. Okay, Rich, I've been using Claude Code, not me. I have been using Claude. But this
you don't like Claude anymore, dude. What's going on?
We can cover that in the appendix. I've been using Claude for months, and I still don't really get what a token is. Why don't these models just work with words like a normal person?
I mean, they kind of do, honestly, man. I think they used to. That definitely used to be the case back in the day. But I think fundamentally people realize that language models don't have to work with words because they're computer models. Computers work with ones and zeros. And so why force them to work with words if they could work with some structure that isn't constrained to being the words that we know and love as humans? So the idea here is basically that language models, when you pass them text, you're feeding them in words, but there's a little process that happens before the model actually sees the words. And this happens behind the scenes where they get converted into almost like a lower level version of words. And these things, known as byte strings, so these are like things that you can use to represent words in computer language, but fundamentally are illegible to us humans. Those things are then chunked by a model into individual components that we then call tokens fundamentally. And so a model nowadays is basically just training on individual ones and zeros fundamentally. Like it never actually sees words, it just sees like a series of ones and zeros. And if you give it enough data, it can learn what they mean, how they interact with each other, and it can trick us humans into thinking that it's actually working with words, right? So that's the short answer. The slightly longer answer to this is that in linguistics, folks have thought about tokens for a long time, and especially in the study of phonetics. So, people in linguistics and especially phonologists, they like to think of these things called phonemes, or if you're a cool kid, phones, they'll call them phones. And it's sort of this base unit of sound that is part of a language, right? So for instance, if you have the word like preschool, folks in linguistics might say, well, preschool is composed of 3 phonemes, pre, sk, and ul. It's 3 sort of like units of sound. And the idea of this is that each language, say English, German, Chinese, they all have these different sounds that are valid in that language, right? And so for instance, right, if I gave you the word like, he zambled up the hill, that sounds kind of legit, right? I mean, I don't know what zambled is, but that kind of sounds like English, right? And I could probably convince you to believe that that's a legit English word, right? But if I told you, hey, he nix babbled or nix nang up the hill, you'd be like, Rich, what are you saying? Did you just have a stroke, right? And the thing is, the reason that sounds like I had a stroke is because the phonemes that I used there might be valid phonemes in German or Chinese, but just in English, we just don't have those sounds. We don't have those base units of sound, right? So anyway, the point here is basically that linguists are super pedantic. They love to think about these little differences in languages that no one in their right mind would ever reasonably want to study, except for folks like myself. And they have coined this idea of like tokens, which basically represent lower order aspects of words. And so they like to think about, okay, how can we decompose words into lower order meanings? And so for a long time, there's like this notion of tokens as like a thing that goes as like a meta class over words has existed. And folks in computer science and in language modeling in particular have repurposed this idea as the things that you feed into a model. So, while we might be interacting with a model, we pass in words into the text. What's actually happening by the model, as I was saying, is that it's processing something that's not text. It's processing these byte streams. And so language modeling scientists will, repurpose, overload this idea of a token to then represent that thing that the model sees.
I'll maybe just add the one additional thing that I always am reminded of is we didn't just arrive at BPE overnight, right? Like it's both coming from this morphology history that you were mentioning.
And you should say BPE is what I was describing. I didn't say this in particular.
Yes.
But
yeah. The acronym being byte pair encoding, which is kind of the technique or the algorithm with which we use to turn a large corpus by observational prowess into these, chunked tokens that actually represent this vocabulary size. And it works by you give it a number of ideal BPE tokens to create. Usually it's on the order of 50,000. And then it reads through a ton of data from the internet and says, okay, these are the most common words. In English, it'd be a, it'd be the, etc. Make those small tokens and then kind of keep doing that for other prefixes. So it's this iterative approach to build up more and more complex ones over time. Very clever. We didn't arrive at that overnight. We tried a lot of other things before we tried that. And in ML modeling specifically, one of the big ideas that kind of unlocked this notion of creating embeddings, which is what those tokens then become, was in the research of word2vec or glove, which I won't go into a ton of specifics on. People can look up or ask some additional questions if they're interested. But I do think it's kind of interesting that when you were using glove, when you were using these old forms of pre-processing to then put into a language model, you would always have to run sentences through some pre-processing layer in order to get them to have the maximum matches to some existing word-based vocabulary. And usually you would then have to do, lemmatization or stemming, where you're trying to take some complicated word, walking, and make it just to walk. Because you kind of want to be able to squint at a sentence and say, if the man is walking or the man walk, that's like kind of the same thing. So it actually, for a long time, we were losing some pretty valuable context and additional linguistic signatures by all of this pre-processing that we're doing. But we were scoring so low on the benchmarks, relatively speaking, that even if you're hacking around it with a pretty brute forced approach, that still let you increase your performance on this benchmarks. I think BPE in some ways, in addition to the whole scaling hypothesis, was one of these ways that we really blew the lid off of benchmarks like glue, because we're actually fully encoding the meaning of that sentence in a vocabulary space that is both kind of intuitive, like yes, roots will still share their base token usually, but it also has all this additional modeling prowess that is more linguistically driven. It was a pretty big unlock in the LM space.
It is. And so what you're describing here is how we used to do it like 10 years ago, right? Which is coming back to what I was saying about linguistics. Like linguists were the first folks to really get into the field of NLP, and they had all these hot takes around how do we pre-process data to be able to train on this data in an easier way. So what you're saying with lemmatization and stemmatization, it's the idea that, if we can basically just train a model on these base units of words, so rather than word like walking, we just feed the word walk into the model and it sort of learns to, understand that, the ing is a certain participle that isn't really required in this case. Anyway, this was all like linguists were like really all over this field and trying to figure this out and do this effectively, but they had to come up with all these different hacks, right? And all these different pre-processing steps to make this work. But more and more stuff just kept coming up. Like for a long time, there was an open question, like how do you deal with like Chinese scripts or other scripts that aren't, just the Roman alphabet? And it wasn't really obvious. Like, how do you feed a Chinese character into the model? And what people realized recently with this BPE strategy is that, if you can just change all words into just series of ones and zeros, it makes it much easier, because now rather than looking at a Chinese character and having to interpret that somehow, you can just change that into a series of ones and zeros and have the model learn on those ones and zeros, rather than using this base Chinese character that might be harder for the model to somehow decipher what, how to interpret that, right? So I think we'll leave it at there. But there's a lot to be said about tokenization. I mean, there's still so many open questions. And I think it's one of these things that's actually understudied. All right, what's the next one? What else do we got? Let's see. All right, so someone asked, everyone brags about context window size. Gemini has 1 million tokens or whatever. What does that actually mean for how I use the model?
People really love competing on size, don't they?
So true, dude. Yeah.
So, yeah, I mean, look, for a while, I feel like that was the main needle that actually the Frontier Labs were pushing, right? Like the first ChatGPT API release was maybe limited to 20,000 tokens, and then it stepped up to 50. That was a big deal. Then it got to 100,000. Now we're talking 1 million tokens. I think Gemini can maybe do 2 million tokens, although the pricing actually changes once you reach a certain threshold, which I feel like is kind of interesting, shows that it's more costly to do that kind for inference. So in terms of what that means for regular people when they're actually interacting with these models, I'd say almost nothing. Like a good implementation on top of the underlying model usually makes it so that it saves some element of the history that you did before you'll have some cutoff if you ever reach that point. But it does mean that the longer your conversation goes, the less fidelity typically that the model will have for what has happened in the past, especially what happened long ago. And this is still an ongoing research of like model memory. How do we record things in a more high fidelity way that doesn't lose this context once you just go out of bounds on kind of this size? So like I said, for what it means, I'd say in the day-to-day, probably nothing. A few things that I do see people doing, though, that I want to call out here is if you only have one chat conversation with Codex or Claude or ChatGPT on the web UI, I would actually encourage people to experiment with opening new chat conversations to do
That can
things.
really help. Yeah.
Like
100%.
often actually, if you aren't really getting the answers that you want or it's not quite solving the problem, starting from afresh actually will completely solve that for you, because conversations that are longer than some threshold just aren't really in the training data for these models. Like it has a lot more examples of conversations that are short to medium size than conversations that are super, super long. There's also just more conflicting signal in that history of like different questions that you've asked it historically versus what you're asking it to do now. And there's a million reasons why your context window can get muddied over time. So I think that's a big thing, actually, is just you typically get better results out of models by keeping the prompts relatively succinct and keeping a conversation pretty tightly scoped to just doing that one thing. And outside of the conversational frame or like the therapy frame, you don't usually actually lose that much by Claude not remembering what
just
you were talking
restarting
to it before.
Right,
Yeah, like
right.
fully restarting it. And I don't know. I think because of that, in part, we've seen less of a focus recently on expanding context windows, and I think the research has shifted into just increasing general intelligence, and then also some of these other techniques that are a little bit more modern, like
Yeah.
training the KV cache or thinking up like personality vectors in memory or more sophisticated RAG retrieval pipelines. But in terms of just like the raw KV cache being able to go to 1 million tokens, doesn't feel like we're really pushing that much further.
Well, I think it's actually important to clarify one point, which I think folks that don't work with this might not realize. If I tell you, hey, my model has a context window of 100 words, let's just say 100 tokens to be precise. To me, that sounds like if I were a layperson, it would mean that, okay, the model like physically cannot process the 101st word. If you feed it another word after 100, there's no way the model could see that word, right? Because it's done after 100. That's not actually true though. I mean, the way that these architectures of these models work is that in theory, a model has a context window of infinity. There's nothing fundamentally stopping the model from seeing, a billion, a trillion, a quintillion words. Now, the thing that might stop it eventually is just that it runs out of memory. But, for all intents and purposes, like that could be, if it's a small model, that could be after, a billion words, right? When people say my model has a context window of 100, it means that they've kind of trained it to only really have a context window of 100. Maybe a good analogy is to think about it like this. Think about a model as a person who runs track, okay? And you talk about folks who are really good at running like 100 meters or 200 meters or 400 or 10K or, marathon runners or ultra marathon runners, right? It's not that like a sprinter who runs 100 meters can't also run a 5K or a 10K, of course. Just keep walking. Nothing's physically going to stop you from just continuing on. But the thing is, if you're a 100-meter sprinter, sure, you can run a 10K, but that's just not your discipline. And you just don't really know how to do that very well, right? You might gas out after like 300 meters because the longest distance you've run in your life is 200 meters, right? So you might just basically after a couple minutes just be completely tired. And for the same reason, like someone who's run ultra marathons might not be a good sprinter. That is sort of like the right mental model to have, even though no one will tell you this. If you actually work with a language model and you download a language model, you can just keep feeding it more words. But if it hasn't been trained to see 1 million words and you feed it in 1 million words, the model will be like, whoa, buddy, I don't really know how to do this. Like, I don't have the capabilities that make me good at understanding how these 1 million words interact with each other, right? So fundamentally, that is what we're talking about when we're talking about super long length context windows. It's these models that know how to deal with a ton of data and can store that data in some efficient way so that you can actually, in practice, feed in 1 million words and it can store all of that and not run out of memory, right?
Yeah, I think that's a great point. It's both the actual hardware itself that these inference clusters are hosted on are running out of memory. I mean, that's like a logical constraint, which is pushed more on the hardware side of things. Like when NVIDIA boosts their GPU memory by 2x generation over generation, that inherently unlocks more context window. Some of this stuff is kind of quadratic, so it's not necessarily it doubles the memory. We get double context windows. Although there's some work on like more linear history that is promising, but hasn't been widely adopted yet. I think the only other thing, maybe to bring it back to something that we have mentioned already in this conversation, is I do think that the concept of things being in or out of distribution is this concept that seems a little scary to people because it comes from these like statistical methods or like looking at data distributions and skews. But I think that the actual like vibe or the meaning behind it and when we use it is often very simple. It's just saying that the model hasn't seen this thing before. You know what I mean? Like these are pattern recognition machines. And when something is in distribution, great, it's modeling that. It's seen it. It kind of knows maybe what to do with it if it's seen it enough times. And it's able to extrapolate just how people do. But if it's something that it totally hasn't seen before, models, unlike people, are actually pretty bad at extrapolating to things based on intuition because they don't really have intuition in the classic way. We try to teach them some intuition, but it doesn't really have it. So in the case of like the marathon example, how that couples to text is just saying, yeah, like we're making decisions when we're training these models or based on the data that we have access to. Here are the examples that we can throw at the model and that are efficient to throw at the model. And here are ones that we don't. And if it's something that it just hasn't seen before, in the case of really long conversations, it won't really know what to do. And I think part of that, maybe I'll just as a footnote in case people are interested in reading more, is it actually used to be a hard limitation of language models that they couldn't go longer than some length because the actual positional encodings that we attach to these tokens were capped at a maximum length. One of the things that has unlocked our ability to do longer context windows is we actually came up with like math conventions to be able to say, let's layer on some uniqueness to different places in this stream because the model itself is not really aware of, this word came first in the sentence and this word came 10th. It's actually some additional things that we're layering onto it almost as a timeline. And until the math that backs the timeline really got good enough, we couldn't even do any of this extrapolation. Like things were locked at exactly the number that we had prefixed to make the math work.
Yeah, we could go into this at some point, but the idea of rotational embeddings has been a massive unlock in this whole field.
Yeah, I think at the very least, and it's also probably not great for an audio medium, but you can look at how rotational embeddings, are called rope embeddings, change with the length that they're operating over, and also often change with the depth of where they are, or like the amount of dimensions in the vector that it's interacting with. So it can come up with this 2D simulation basically of how these things can interact both over time as well as over dimensions. And at least visualizing that is super interesting. Like it shows a little bit how this like math really plays out on a broader scale. And there's some like locality to it. There's some like globality.
Here's a good way of thinking about it. If you want to imagine a word embedding, the way I kind of think about it is, the double helix in DNA, in these like biology simulations, you have
shout out Rosalind Franklin.
Yeah, shout out Rosalind Franklin. You have like these little like helixes that are kind of floating in space. That's kind of the right way to think about word embedding, sort of, as like these like little helixes that kind of like spiral around each other. If something's flat, it only occupies one dimension fundamentally. But as soon as you get it to like spiral, it's basically occupying this like other plane that unlocks many more axes where it can live in. Okay, we can leave it at that fundamentally.
I like that.
Right?
I like that. No, that's good. Richard, I have another question for you.
Sure.
Let's pop some stacks from the modeling internals. Agent seems to be the buzzword of the year right now, but I swear it means something different every time I hear it. Can someone just tell me what actually qualifies as an agent versus a chatbot with extra steps? And can that person be you, Richard?
That's a really good question. I don't think there is a really good answer to that, for the simple reason that as LLMs have gotten better, I think what it means for an LLM to be an agent, the bar has kept going up. And so maybe I should say this. I mean, basically 3-4 years ago, there was this paper, Chain of Thought Reasoning, that came out where for the first time we realized that, hey, models could actually start introspecting and reflecting on their own output. And that was a pretty big unlock because that meant that models could, as they're saying stuff, also think about what they're going to say. So they have this notion of being able to plan and to reflect on themselves. And once models could do that, I think we all kind of jumped the gun a little bit and we were like, oh, wow, these things are self-reasoning now. This is AGI, right? And we thought of them already as these like independent agents and processes that could kind of go off and think for a long time. And then a year later, people realized that, hey, not only can models plan their answer and introspect on their answer, they can also realize when they don't really know how to answer something because they just haven't been trained on that data before. Like, for instance, if you ask a model, hey, what's the weather like right now in San Francisco? A model won't know what the weather's like because it doesn't have access to like the online ability to query the weather channel and figure out what the weather is. And so people realize, well, what if we could somehow give models, in the instances where they realize that they just can't answer it, access to the internet effectively, right? Like external APIs that they can call on to get the information that they know they don't have, ingest it, and then feed it back to the user, right? And so a big unlock here was like the idea of these MCP servers, where you could basically give a model access to a whole host of different tools, and the model can reflect during its output process which ones of these tools it wants to use. And now, basically, I think the idea of an agent is a model that can plan, can reflect on its own behavior, can know when it doesn't know something, and then query an external tool to figure out the answer. I think that that is now what you would call an agent. But as said, I think the bar keeps going up as models keep getting better and better and better, right? And maybe in 2 years from now, the definition of an agent will be something that can not only do all of that, but can also somehow access external hardware in some way. Like maybe an agent is something that can, in the future, do all of that and also then figure out that in order to satisfy your request, it has to get your Tesla to drive to the supermarket to buy you the thing that you want and then come back to your house and deliver it to your doorstep, right? As models keep getting better and they can access more of the tools that we have online and in the physical world, I think the bar for what an agent is keeps increasing.
I think that's right. I think maybe one other way to think about it, because I think right now the frontier providers are trying to converge the two meanings, right? Like they already have the brand recognition with ChatGPT and with Claude Online, that they want those to become agents. Like, you know how you can turn on agent mode when you're in chat, or Anthropic just rolled out Claude Cowork, which is intended for people to use the Claude desktop app, but do more professional things with it. Like you can drop in different files and give you some outputs, work on your file system, kind of like a Claude Code for business, non technical folks. And I'm sure we'll cover that in a subsequent episode to see how we like it. But I think the thing with agents that I would really say is like the demarcation of a chatbot and an agent is that an agent chooses when to stop and a chatbot doesn't. Like a chatbot, the contract between you is very much you give it some question, and maybe it's doing a lot of those things behind the scenes, Richard. Like maybe it is calling some tool calls, maybe it is crawling the web or pulling some RAG retrieval on some data, but it's synthesizing you one message at the very end to say, this is what I'm coming back to you with. And at least in my mental model, I'm sure people can disagree with this, I still wouldn't really define that as an agent. I think it's more helpful to describe that as being a chatbot interaction, whereas an agent almost implicitly in your ask to the agent is to tell it when to complete, work on this coding challenge until these unit tests pass, or write this file, and until you're done writing the file, don't stop. You know, do what you have to do to get it done. And I think that notion
takes,
of a little bit,
yeah,
do whatever you need. Just don't
yeah,
rm-rf my file system.
right.
Pretty please. So I think that notion of like autonomy is kind of critical to thinking about agents as a separate thing. I would say the other thing as well is, in my mind, agents are these long running tasks that could potentially go for multiple hours at a time. And I think in that way, it's a little bit more useful to think about them as these asynchronous bots or agents instead of chatbots, which you kind of are still expecting to be largely in the loop for, even if it's doing some work for you. But they're converging. And I think that that's the latent point, is like they converged or are converging in 2025. I think they're going to continue to converge in 2026. But the underlying models that power agents and power the chatbots are really the same. It's just exactly how we're instructing them that ends up being a little bit different.
Yeah, it's like a UX experience too, right? It's like kind of like the difference between thinking of an LLM as a chat interface and thinking of an LLM as a coworker. I think people like to separate these two things out into these two categories. But fundamentally, like the technology backing both of these is just an LLM. It's just how do you interact with these things that makes one thing an agent and one thing a chatbot, you know? I think the bar is going to keep getting just exponentially increased every year as we see that these models are getting better and better and better. And as said, I'm waiting for the time when these models can not just query the internet, but can query the physical world in some way to solve some task.
You're waiting for the robots.
I think it's gonna happen, dude. You know, I really do. Let's pick one more good one to wrap up this app. I'm curious about this here. I wanted to ask you about, have you heard of the residual stream? Someone is asking about what is the residual stream?
Oh, wow. This is in the weeds. Yeah, I think it's cool. Let's do it. So the idea of the residual stream, I think, comes out of a paper / research that Anthropic did and published last year that kind of introduced this concept into the mainstream. And it's a way to think about how data flows within a transformer architecture, or maybe a neural network more broadly, but especially in language modeling. I kind of think about it like this. We have some input, we have some question that we want to ask some chatbot, or maybe it's a prompt for it to work with code, write some new file, whatever. I send it some message, and that is all encoded in the tokens. This is actually a good last question. It encapsulates a lot of what we've talked about in this episode already. So we encode it in tokens instead of words, right? And then we feed that into the model. And we know what's going to happen next is that the model's going to give us a probability over tokens, over the next token that comes in that sequence, which is going to be the first token of its answer. And then we recursively run that, and then it builds up first, second, third, fourth, all the way till it's done generating tokens, and then returns that result as text to us. That's how it works. The residual stream I think of in actually very physical terms, where if you have some river flowing, and at the top of the river, it's maybe the Great Canyon, then you are at the very top, you're at the peak where the river begins, and then you throw in all of the initial prompt that you've given it. You toss in the tokens, right? And there are people standing downstream of that river. And each of those people can choose to do one of two things. They can either observe what's happening in the river, or they can put more things into the river. And that kind of gets to this idea of reading or writing into the residual stream is what these people are doing. So if they're observing what's happening within this river of what you've given it, maybe they have some additional piece of information that they want to give that's helpful to the person downstream. So they throw a little bit of things in. And importantly, with the residual stream, why it's a residual at all is because the original tokens still float down. It's just there's some additional things that people have thrown in as it's going down this pass. And in mathematical lingo, that corresponds to the fact that at each subsequent layer of this neural network, of the transformer architectures, what we're literally doing is saying the next layer is going to see the inputs that I got to my layer, as well as the manipulations that I've done to them via this plus operand. So this was, introduced in the original transformer paper. You kind of think of it like y equals f of x plus x. And I have control over the f of x, which is the additional information that I'm adding or writing to this stream. But it still gets the y, which is the next layer, still gets this initial input x. So that's how I think about it. And the residual just comes from that fact that we're having the residual element, which is that input to the layer.
Yeah, I think that's a great analogy, honestly. I think the way I think about it, maybe to keep building on your analogy, is like, those little paper boats that kids play with? Like you can throw them into a little lake and they're kind of like bobbing in the water. Imagine that like every word that you have initially that you feed into your model is like a little boat, right? One of these little like paper boats. And you throw them into this big river at the top of the canyon, right? And all these, let's say you have 100 words, you'd have 100 little boats that are floating in this river, kind of like bobbing up and down in the current. And every so often, as you said, like there'll be people on the banks of the river that will like basically pick out some of these little boats, maybe tweak them a little bit and then throw them back in the river, right? And they keep bobbing up and down. And these boats, because they're just floating, they're kind of like mixing along the current, right? They're getting pushed left and right, and they're kind of like bumping into each other, moving to the right, moving to the left. People keep picking them out, putting them back in. And so after doing this, after traveling down this river for a mile, the order in which the boats end up after a mile is going to be completely mixed up, right? Boat that started at the left of the river might now be at the right. It might have bumped into a bunch of different boats along the way. Maybe someone had picked out that boat and like tweaked it a little bit and then put it back in the river. So they'll be like in a huge jumbled kind of mess, right? And they'll kind of have bumped into each other, influenced each other a little bit. And at the end, these boats will emerge. And what emerges is basically what we think of as the output of an LLM, right? It's like this like whole jumble of different words. And what the LLM learns is basically the LLM is this river. It's this current that basically the model learns for how to mix these different things in different orders and when to pluck out a boat and when to put it back into this river, right?
Mm-hmm. It's everything that happens downstream. It's the river, it's the people that are changing these boats, and it's the output that's then trying to disassemble what these boats mean for them.
Exactly. And so the folks at Anthropic love thinking about the residual stream because it turns out that if you look at certain parts of the model, the river is long. It's like a mile long. And so the question is, well, if we want to understand what is happening in this model, we have to pick out, we can't look at the whole mile of this river. We can only look at that little segment of it, right? There's like too much to look at. And so what are the interesting segments to look at in this mile long river? Well, it's the parts where there's people on the banks of the river taking out boats and putting them back in, right? Those are like some of the interesting moments that occur in the model. And it turns out that those are sort of these like key moments where interesting things happen in the internal of the model. And you can analyze what's happening at the river at that particular point. And it's actually very informative of what the model thinks is currently the most important thing to focus on in the process of learning language, or metaphorically, like in this river. Like those are really important moments because they influence how the boats will like bump into each other going forward, right? The folks at Anthropic use these like key moments and will analyze the crap out of them because like interesting things happen there, right? So they'll figure out that, hey, like 3/4 of the way through this river, that's actually when the model learns that Paris is the capital of France, right? So there will be like these like key moments where here we see exactly when the model figured out what an adjective is, and here we know exactly when a model figures out what a Chinese hot pot is, right? There's all these different things that you can look at, and so that's why it's kind of useful to think about a language model as a river, because you can really like hone in on particular zones that are interesting in this learning process. We could do a whole segment, honestly, on this. I love this idea of a residual stream. I think it's very metaphorical, and I don't know, it's cool to, you know how like physicists will have like big insights when they think about complicated math in terms of like biological or physical things that they can like mentally visualize. I think that's actually kind of what is so useful about the residual stream. When you have this mental imagery of a river, I think that kind of helps you interpret what is actually happening. This is like a new idea that's popped up in the last couple of years.
Totally. I mean, sometimes it's these framing ways of simplifying the math that actually lets us think about things in a different way. Could you apply some fluid dynamics algorithms to a transformer? Maybe that would be helpful. I would not have thought about that if I didn't really think about these data flows. There's also a lot of bridges to like, the actual read and write matrices themselves, like how that relates to sparsity. I'm actually in the middle of a research paper right now that's trying to kind of untangle some of the sparsity relations that are a little bit more geometric, which you can do once you start thinking about this residual stream as these read write matrices. So yeah, residual streams are super cool. And I feel like it probably is worth doing a slightly more in-depth look at this, and maybe coupling that with some of the mech-int stuff that Anthropic is also really known for, because I think they both come from the same underlying field of research, which is trying to get to know the internals of these models better, both so we can improve their performance, but also so we can make sure that nothing suspect is happening under the hood.
Yeah, it's really cool, dude. I feel like Anthropic, I would give them credit for a lot of things, but I would give them especially a lot of credit for coming up with these really good metaphors for how to think about neural networks. Because fundamentally, we've always thought of them as black boxes, and I think people have been really afraid to delve into them because it's fundamentally kind of impossible to decipher this tangle of ones and zeros. But yeah, having this insight that you don't have to look at the entire black box. If you just zone in on this one tiny moment, that is actually the most interesting thing to look at. Then that makes it feel a little bit more manageable, because now you're not looking at trillions of ones and zeros. You're only looking at 1,000 ones and zeros. Or millions, and that's a little bit more doable,
Yeah.
So kudos to them, man. Well, boss, I think that about wraps it up. I love these questions. These are seriously like some solid questions.
Yeah, me too. Shout out to everyone that contributed. Sorry we couldn't get through them all.
There's definitely a couple we missed, but we'll get to them.
There will be more listener mailbags in our future, so we'll keep them coming.
We'll definitely get to them. Yeah. All right, man. Well, I'm excited to see you in a week. I'm super stoked.
Can't believe it. Yeah, safe travels.
I know,
buddy.
me neither, man. Thanks, man.
Hope the last week in London is everything you've dreamed of. But San Francisco is putting on a show right now. So, well, in that case.
No, I'm excited to see you though, and it's gonna be awesome, dog. I can't wait.
Same here, man. Well, we'll be in studio. Side. Yeah, the next podcast. Awesome. I can't wait for it. See you then, buddy. Cheers.
Sounds good, homie. I'll see you soon. Bye.
Later. I got a bit about this field day that we were doing yesterday. So the first thing is these picnic benches at Chrissy Field get super busy, right?
Oh, yeah,
and
those are great.
It was supposed to be a good day. So we were like, oh, we got to lock this thing down
100%.
early so it'll be ours by noon. We needed one of the like 4 with a grill.
Oh, the premium option,
so
dude. Okay.
The premium, dude. Only the most sophisticated of park connoisseurs.
Yeah, of course.
I posted on TaskRabbit.
Oh,
and I
no
asked
way,
for a
dude.
guy to just show up and sit there. And it turns out this is a category on TaskRabbit, dude.
Oh my
It's like
God.
people who are professional waiters.
Huh.
Not to like wait on tables, but to
Uh-huh.
like wait at places.
Huh.
So I hit up this guy, Kenneth.
Yeah. You
But
should do
anyway,
like a
so-
technical interview, you know, to check his
That's
skills.
right, dude.
Just have him sit around is what I mean. You know what I mean? Tell him that you're
Oh,
going to
yeah.
interview him at like 5,
Yeah.
and then you bring him in at like 10.
Make him
And
wait,
then if he's
dude.
still there, you're like, you passed.
You
know?
passed. You Congratulations. You have the
Congratulations.
next. Do the
Right,
same
right,
exact
right.
thing, dude. No notes. Just do this tomorrow at the picnic
Right,
benches.
Right.
I then Ubered to Chrissy Field. I show up. I get out of the Waymo.
Kind of
and
not
there's
there.
just there's just no one else there, bro. It's Kenneth sitting on a picnic bench, and there are 0 other people sitting on any other picnic bench. So I was like, hey Kevin, dude, crazy there's no one here, man. Has it been like this all morning, or did I just like catch a minute? He's like, no, dude, I haven't seen a soul since 7 a.m. You're the first person that I've talked to today since I've woken up. And I was like, sick, dude, sick. That's amazing, dude. I'm really glad you were holding down the fort. Yeah, dude. So that was $150 well spent.